Star clusters are deceptive in their simplicity. By and large, they are just stars against the background, just like this. But if not developed carefully, the close proximity of those stars makes for an extremely bright core, which can easily be blown out in the development process and is often misinterpreted by development software as an artifact that I refer to as light worms. Light worms are the patchy hazes of light that you see around the core of the star cluster. And I call them light worms because if you look at them closely, you can see they often appear to bend and turn. Light worms happen when the developing software interprets small, barely visible stars that are in very close proximity to each other as dust and gas. And star clusters not developed carefully also get the second phenomenon of an extremely bright core where the individual stars are lost to brightness. In other words, the center part of globular star clusters is frequently blown out. But one of the interesting, nearly universal features of globular star clusters is they contain very little gas or dust. There isn't much in them in the way of nebulae and star-forming regions. In fact, the stars in most globular star clusters were formed not long after the beginning of the universe, about 12.5 billion years ago roughly. And if we zoom into them, we just see stars on top of stars on top of stars. They do go through a process known as core collapse, however, in which, over time, the stars get closer and closer to one another. But no matter how much we zoom in, we should see more individual stars. But despite their simplicity, the fact that star clusters are just dense groups of stars, they can be surprisingly difficult to develop. Light levels within an image of a globular star cluster ranges very quickly from almost total darkness at the outside of an image to completely photon-saturated pixels or blown-out regions at the center of a star cluster. But the cores of star clusters can be revealed in development, and how this is done is as much a matter of imaging technique as development. Let's take a look at how it's done. The first thing to remember is that when shooting the cores of star clusters, use short exposures. It is especially important to use short exposures when shooting any DSOs that have widely varying regions of darkness and brightness. Shooting short exposures will allow your camera sensor to collect photons without the sensor's individual pixels or photosites becoming saturated. Saturation happens when all of a camera's photosites or pixels become filled with as many photons as they can hold. When a photosite has no photons, it's interpreted by the camera as black, and as the photosite is exposed and collects photons, the black goes through various brightening ranges of gray until it finally reaches white. Once it reaches white, it can't collect any more photons, and if too many pixels collect photons, no detail can be revealed because everything is just white or some close shade to white. So the information there, the detail, is lost. Shooting short exposures allows your camera to avoid losing detail or information by keeping exposure time short enough that most of the pixels do not become saturated. In Nina, you can use the information in the Statistics tab to test the quality of your exposure. For me, the most important parts of the Statistics tab are the graphical representation of the histogram itself and the minimum and maximum sections designated min and max right here. Now the min and max readings portray a lot of information, and they refer to what are called ADUs, or analog to digital units, which are how your camera measures between full dark and full bright. However, we're not going to get too technical here, this isn't the right video for it. Just note that the minimum represents the darkest place on the image, and the number beside it in parentheses with an X beside that reveals how many pixels are at the minimum value, or rather, how many pixels are at the darkest point on the image. And the number on the right represents how many pixels are at the brightest point on the image. So right now I am shooting with my Player One Aries M camera, which has the Sony IMX533 sensor with an exposure time of 60 seconds. And I am shooting just a hair over unity gain at 130. And the minimum and maximum reading means I have 4 pixels at the darkest point, and there are only 3 pixels at the brightest point on the image. And for a globular star cluster, that's really good. That means very little information within that globular star cluster is going to be lost to brightness, crushed in white, or in other words, blown out. Now, let's take a look at the graphical representation of this image, the old faithful histogram with which most photographers are familiar. As is typical when shooting astrophotography, pretty much the entire light curve is constricted over to the left side of the histogram. And I know some persons would look at this light curve and say, no, that's a problem because your light curve touches the left side of the histogram. To be honest, I don't care about that, for a number of reasons. One, I have an offset set, the camera's default offset of 35, and that's going to prevent any pixels registering at the dreaded 0, where the camera makes mistakes and creates noise and such. Two, is integration time. As I shoot image after image after image, photons will be collected, and that information is going to add up in the final stacking. And three, as far as I'm concerned, what really matters is A, the right side of the light curve does not bunch up against the right side of the histogram, which would mean that all the information is being crushed in whites. But that's almost never a problem for astrophotography. And B, I do not want the light curve's peak to touch the top of the histogram, or, if it must, as little of the peak to touch it as possible. And since my max ADU tells me only 3 pixels, or whited out right now, fully saturated or maxed out with photons, that means barely any of the top of the peak of the light curve is actually touching the top of the histogram. And for shooting astrophotography, it's that peak that I'm really concerned about. The more of the peak of the light curve that is touching the top of the histogram, the more that means you're losing information to being blown out in white. And right now, for shooting a globular cluster, where my goal is going to be to reveal as many of the stars in the interior of the cluster as possible, since I know from looking at the max ADU that only 3 pixels are technically fully saturated, this exposure is pretty close to ideal for a star cluster. After several hours of imaging using 60-second subs, and following some pretty aggressive calling using PixInsight's subframe selector to get rid of all but the sharpest subs, I was left with 150 odd subs, which I then stacked in PixInsight's weighted batch preprocessor. And as is typical for me since I live at a dark sky site, I shot in LRGB. And the processing left me with 4 masters: luminance, red, green, and blue. Since a globular star cluster is a collection of stars, the first thing I want to do is make sure I have the best stars possible. So I'm going to deconvolve them using Blur Exterminator. A standard procedure for me using Blur Exterminator is to run it first in the correct mode and then in the default mode. This helps ensure that any stars that may have been affected by optical aberrations are corrected, and then all the stars are properly deconvolved and made sharp. Once the Blur Exterminator has done its job, I'll use the Star Alignment tool to align the RG and B masters to the luminance master. Then I'll use the Statistics tool to find the RG or B master that has the highest median, open the Linear Fit tool and use that image as the reference image, and apply the Linear Fit transformation to the other 2 images. In this case, the blue master will be applied through Linear Fit to the red and green masters. Now in my usual workflow, I combine the red, green, and blue masters separately using the Channel Combination tool, remove the stars, stretch and denoise them, and then recombine them later on in my LayerBased photo editor, Affinity Photo. But with globular star clusters, we're working a very delicate balance between an extremely bright core and a very dark outer region. So I want to put as much of the information together as soon as possible as I can. So with globular star clusters, I'm going to combine the L, R, G, and B together using the LRGB combination tool. Now you can see that we have a very rich image here. There are lots of stars and lots of fine detail, from the smaller fainter stars near the core of the cluster and practically drowned out by its brightness, to the near infinitesimal stars near the outside of the image. But as you can see, there is a tremendous amount of haze in those artifacts that I call light worms within the image, obscuring fine resolution of the core. Fortunately, we have the technology to remove that haze. And I'm going to do something that at first guess would seem nonsensical, I'm sure. I'm going to run the Star Exterminator on the star cluster. It's got to be nuts, right? I mean, a star cluster is just a collection of stars. So if I run the Star Exterminator on it, I'm literally taking the stars out of an image that's just stars. But hang tight and watch what happens when you run the Star Exterminator. However, before we do that, there are a couple other things that have to be accomplished first. Right now, the image is unstretched and I haven't dealt with the noise, so let's do that. I don't generally like using the screen transfer function to stretch the histogram from most DSOs. However, I do find it does a wonderful job with stars. So I'm going to apply PixInsight's screen transfer function to the star cluster image, then transfer that stretch over to the histogram tool, and then apply that histogram transformation to the image to make that stretch permanent. Then I'll remove the effect of the screen transfer function from the image, because as of this time, the image is properly stretched for the stars. Then I'm going to run the Noise Exterminator. This is done after the stretch because Noise Exterminator gives you your best results once the information has been stretched. And it's going to remove that grittiness from the image and just help smooth things out very nicely. Here's the image after noise exterminator, and before, see the grittiness, and then after noise exterminator again. And now, let's work some magic. I'm going to get the extraneous glow and the lightworm artifacts out of the star cluster by using the star exterminator to remove the stars from an image that's nothing but stars. To get the best results from Star Exterminator, be sure to click the Select AI box and select the Best AI. And be sure to have all three boxes clicked: Generate Star Image, Unscreen Stars, and Large Overlap. Unscreen stars will give you better results when removing stars from an image that has been stretched. And Large Overlap tells the AI to be basically more thorough in considering how it removes the stars from the image. It takes a few more seconds, but it does a better job. And the Generate Star Image option is absolutely necessary because we need that star plate. Alright, let's speed through the remainder of this. When the Star Exterminator is done, we get an image with just stars. And while at the moment that image might look unnatural, you can see the detail of the stars almost all the way down to the core of this very bright globular cluster. And in the other plate, we can see the haze of light in the light worms. We're going to save both of those because they'll come in handy in later processing. I'll just save them as 16-bit lossless TIFFs. Now, if we were to process just that information, we would get detail, but it would be rather colorless. And that's because the luminance plate was added too early. I added it to get the benefit of its additional information relating to brightness. Adding it revealed the very faintest stars and the deepest stars within the star cluster. But adding it so early has the effect of washing out some of the color. So to compensate, I'm going to make another master of the star cluster, this time using only the R, G, and B masters. I'll just combine these in the channel combination tool, stretch the image using the screen transfer function and histogram tools just as before, denoise the stretched image, and then separate the stars from the background using the star exterminator also just as before. Now it's time to do more advanced developing in a layer-based photo editor. I'm going to drag in as a foundation layer the LRGB star plate. Notice how this is virtually the opposite way you would go about processing a normal DSO, where you would drag your star plate in last, and not usually till all the other developing was about done. And now I'm going to drag in the LRGB starless plate. That's the light haze, light worms, and other artifacts that I extracted out to use in the star exterminator. Using the snap tool, I can quickly align this over the original plate. Now I'm going to recombine the flawed starless plate, but on my terms. I'm going to go through Affinity Photo's extensive list of image blending or compositing modes and find the composite mode that puts this information back into the star cluster advantageously. One of the beauties of working with a layer-based photo editor like Affinity Photo is I can see the results of each composite method as I work. It's all done live. Unlike in PixInsight, I don't have to guess how a process might affect an image, run the process to see what it does, and then decide if I want to undo it, which is very time-consuming if you are determined to get the best possible results. For the moment, the screen composite mode seems to do the best job. Screen simply adds information to information between layers. So all the light in the starless plates is being added to the star plate below. Now I'm going to do something I forgot to do a moment ago and rename the background plate. I'll just rename it LRGB stars. And then I'll duplicate the plate and turn off the original plate. It'll just serve as a sort of foundation, a base point to return to if the editing procedure messes up and I need to go back a long way. Now the next thing I'm going to do is add the RGB star plate. And I'm going to place that layer right over the LRGB star plate layer. And then screen those two plates together, which will give me all the color of those RGB stars and very importantly the brightness of those stars, so that they really stand out against the light haze and the light worm artifacts. At the moment, I've turned off the layer with the light haze and the light worms so that we can better see the results of adding the LRGB and the RGB plates together using the screen composite mode. And as you can see, this gives us glowing, colorful, piercing stars, and they will stand up against that powerful light haze much better. Now we're going to go ahead and add the light haze, and I want you to watch what happens to the image, because the light haze isn't useless, we actually need it. Remember, the light haze is made by the camera confusing stars that are small, densely packed, and faint for haze. And when we turn it on, we can see some of those stars resolving. If we turn it off, those stars vanish. I don't want to lose any stars in the star cluster. I want to preserve every possible star, including those that are out in the light worms. The haze also preserves a small galaxy down at the bottom of the image. I'll turn the haze back on and you can see it here in the circle. I absolutely want to get rid of the lightworm artifacts because they simply don't belong in a star cluster. Star clusters, by and large, don't have much in the way of dust and gas within them. And I need to remove the overwhelming brightness at the core of the star cluster, that light haze that is retained within this layer, but I need to do so subtly in a way that preserves all the detail within this image. And even this little faraway galaxy down below. And happily, there is a way. You just have to go about it with a gentle touch. And the way I'm going to do that is by first placing a mask within the light haze layer. I'll select the starless layer where the light haze and light worms are, and then left click on the mask icon. Then I'm going to select the mask layer by left clicking on it, and then right click on the mask icon down below, and left click to select the luminosity range mask. I will then drag the luminosity range mask into the mask layer, and this will allow me to select what ranges of brightness and how much of that brightness I want to keep from the starless layer where the light worms and the central haze of brightness are. In a lot of ways, this works like adjusting a curves tool. By drawing down on the left side, I'm operating in the darker regions of the image, and here I can reduce the effects of the light worms within the image. And then I can draw down on the right side, affecting the brightest side of the image, reducing the overwhelming brightness of the haze in the core of the image. And I can make adjustments to the interior of the curve, just like with any light curve, just by clicking and dragging on it. However, what's different between using the luminosity range mask and the masks to do this, as opposed to just a curves tool, is that drawing down on the luminosity mask actually renders that information transparent. So you aren't just minimizing things like the light worms from the image, you are making them vanish. And as you can see with the completion of the adjustment, we have no more light worms. And the brightness at the core of the globular cluster is much better contained. But because we have restricted only the darker regions and that very, very bright information at the core, we have been able to preserve all the stars, including the very faintest stars and the nearly amorphous ones that were brought back into the image by adding back the starless layer. Now you can put more than one luminosity range mask within a standard mask. So I'm going to open another one and use this one specifically to adjust the very brightest luminosity within the image, to draw down the bright light haze within the central core of the globular cluster even more. I want to preserve it enough to show that special glow that is found within the cores of globular clusters where tens of thousands of stars are so closely drawn together. But I don't want it to dominate the image so much that those stars at the core are lost. So I'll quickly get another luminosity range mask in the right place just by duplicating the one that I already have, and then I'll begin reworking its effects. I'm going to adjust the dark side of it to have it just very slightly further reduce any effects that may linger from lightworm artifacts. And then I'll draw down just a little bit on the right side to further reduce the brightness of the extremely bright haze of light at the core of the star cluster. And to do this, I'm going to zoom way in so that I can see when those stars at the core become visible. Like I said, I don't want to totally remove that core haze. It adds a kind of special luster to globular star clusters. But I do want to reduce it to the points where those individual stars can easily be made out. And that pretty much does it. Now, unfortunately the space is too blackened, and on many monitors that would show up as banded regions, where the space looks divided by distinct patches of slightly varied blackness. So I'm going to get a little fancy with my first luminosity range mask, and just lift the bottom of the curve up a little bit. This will allow the space to show up as a little brighter than absolute black. But notice how the luminosity range mask angles down from the far left side into the left side quarter. The space is the darkest thing in the image, so it is affected by changes on the far left side of the luminosity range mask. Lifting that side of the curve allows space to show up brighter, but the light worms are in the shadow column to the right, and they remain invisible. Now the only problem is creating those masks weaken the view of the little galaxy down here, and I want to get it back. There are all kinds of ways I could get it back, but I'm just going to use the simplest. I'm going to duplicate the LRGB layer and drag the duplicate to the very top of the layer stack. Then I'm going to unfold the layer and delete out the mask and the luminosity range mask that were included with the duplication. Then, just to keep all the layers straight, I'll rename this mask LRGB Galaxy. Then, with the LRGB Galaxy layer selected, I'll click on the mask icon to create a mask within that layer. Then I'll invert that mask, which will make the LRGB galaxy layer invisible. Then off on the left, I'll select the paintbrush tool and the white color, which will erase out the effects of the mask. And I'm going to erase out its effects in a small region around the galaxy. I have the brush set for a hardness of 0, making for a very soft brush that will allow for a gradual transition of light from the galaxy to the space around it. Then within that mask, I'm going to open up another luminosity range mask. And since the galaxy is brighter than the surrounding space, including the region that I painted since I used a very soft brush, I can slowly draw down on the luminosity range mask, softly removing the surroundings from the image and leaving only the galaxy at the core. This will leave the galaxy in a very nice, refined finish. Then there's just a matter of a little cropping to clean up the edges, and the image is done. The final result is a finished development that reveals the dark, dustless, and gasless space around and within NGC 7078, this globular cluster with a particularly dense and bright core. And while at first glance, especially in contrast to the surrounding space, it might look as if many of the central stars have been lost in brightness, otherwise known as white crushing. If we go in close, another reality is revealed, and we can see that the stars deep within the bright haze have been preserved. Thank you for watching, and I hope this video helps you to improve your own development of globular clusters. It's December 22, and we are totally snowed in here at our backwoods Canadian homestead. So from the snow-covered woods of the Great White North, we wish you a happy Yule. Now get out there and shoot the sky.